Good afternoon, and thank you for allowing me to present today. My name is Lance Schreiber. I'm a remote student from Fort Myers, Florida. I drove up here today to the beautiful UCF campus to give you a big body, to go along with the voice in my presentation for our research methods class. Today's presentation will be on an article that I found called Systems Engineering, the U.S. Education System. I'll explain how this literature review goes very well with a research topic that I hope to do. A little bit of introduction about myself. My favorite thing to talk about is myself. My education. I am a PhD student in the systems engineering track right now. My background comes from my bachelor's in chemical engineering. I received a master's degree in engineering management from UCF about 13 years ago, and I'm back for more. Most of my professional career, of course, though, is in teaching, education. I started off as an instructor at the Naval Nuclear Power School, where I taught math and chemistry to our nation's fine young sailors out running our nuclear-powered ships and submarines. I also was an adjunct professor at Edison Community College in Fort Myers. I spent a lot of time in private industry, consulting, doing technical training, specialized private training as well. And most recently, for the last 3 years, I have decided to take on our nation's finest high school students as a math and chemistry teacher in the public and charter high schools. Question comes up though, why are some schools more successful than others? I've seen a lot. I've seen a lot of different types of schools, a lot of different age levels. And the answer, I think, is very simple. There are small subsystems that just seem to work. Small subsystems that produce a better product. So there comes a bigger question. Can this be applied to that big box system? Those high schools of thousands of students all dropped in to do the same thing. Can we improve it by looking at it a different way? Instead of educators, what if we let an engineer take a look at this? So I've started my goal research to take a look at both of my passions, systems engineering and education. Systems engineering, first of all, history, it's been around for a long time, since World War II. Two main reasons we look at systems engineering. Number one is to come up with an innovative new system out there, something that has a need in the world, or to improve an already existing system. Obviously the area I'm going to take a look at. We hear the word system used quite a bit. More recently, they've started looking at systems of systems, digging down a little bit deeper. What makes the big system work are a series of smaller systems. These things are beyond the control of the original designer, and so they have to be looked at in a little bit of a different way. In addition, we started taking a look at new and dynamic methods. And the area I'm going to look at is basically, can you take these methods of systems engineering and apply them to complex human systems, things that don't have distinct lines, walls, inputs, and outputs. The U.S. education system, as it's called, is probably the most complex system in the world. Interactions are all human interactions. Look at the typical high school student. The things that they interact with are all other human-related environments. It is definitely one of the most complex systems in the world if you look at the number of components and people. With 15,000 public school districts, 3.2 million teachers, and 49 million high school and elementary students, we get to a whopping 70 million total if we include the private schools and colleges. Definitely a difficult challenge to embrace this entire system. So how are you going to do it? The diagram can drive you crazy just by looking at it. It's so complex. There's so many ins and outs, ups and downs. Nothing flows in a smooth pattern. It's very hard to test. Why? We don't know the outcome. And these are children's educations that we're talking about. And there's always a social stigma about experimenting with children. You can't define it. The boundaries, the system, the edges, what goes in, what goes out, what are the subsets, how many are there? So difficult to define. Then you have the needs and the problems. You need expertise. Well, who's the expert? Is it the educators or is it the engineers? Is it both? They need to work together. There's very few physical interfaces. It's not like redesigning the iPad, which is one of our projects. There are no inputs, outputs, things that are easy to understand. The existing architecture, it's different everywhere you go, from state to state, from school to school, from grade level to grade level. The architecture's all over the place. And one of the toughest things is the dynamic model that you have to use. If you change one thing, it's the butterfly effect. It's going to change everything else down the line. So how do you remodel it? If you change one thing, how do you predict what's going to happen? And that change, how is it going to affect further changes? Very difficult. So one of the unique things that I saw used in this literature review was they used student teams. Why students? Why systems engineering students? Well, they're more eager. They're more willing to think out of the box. And we can incentivize them a little bit more, as you'll see. All right, so what are the objectives? This literature review. System engineering the U.S. education system. Well, the Business Higher Education Forum came out with a dramatic quote. Advance innovative solutions to the nation's education challenges in order to enhance U.S. competitiveness. What's this mean? It means the United States was falling behind. The powerful United States is no longer a leader in science, in mathematical, in innovation. There's a shortage of STEM students. Science, technology, engineering, and math. So they came out and said, we're no longer a leader in scientific developments. What are we going to do about it? Well, they had a goal. The goal? To double the number of STEM degrees in a 10-year period. Raytheon took on this challenge. The original purpose, the CEO, Bill Swanson of Raytheon, said, can we use the same things we do in aerospace and military and all these government things and apply them to this U.S. education system? Pretty novel idea. In fact, if you look in the NCOSI database, very, very few applications have ever been applied to it before. His goal? To identify some potential improvements that would increase the proficiency and number of people in STEM to meet that goal that the Business Forum had set out, to double the number of STEM degrees in 10 years. So how are they going to do it? Well, they set up the Systems Engineering Technical Development Program. The student teams that I mentioned. 4 project teams, 5 students, going to spend a couple hundred hours over 10 months, and you can win a prize. That's pretty cool. A lot of students will go for that. And their goal was to come up with innovative ideas, a diverse set of ideas and methods to increase the number of science, technology, engineering, and math degrees. They had to come up with an effective approach to solve this problem. Now, after all said and done, the leaders of the project could then incorporate the best methods from all of them and come up with an overall solution. But to win the prize, you had to come up with a solution. And we're doing this by an engineer's method. Systems engineering process, the NCOSI handbook. We're going to set up requirements. We're going to establish a procedure. We're going to follow a systems engineering method to redesign the system, not just educators and legislature, and this many students have to do this many things and take this many classes, but let's look at it from a systems engineering perspective. So what happened? They almost did it. They almost did it. The winning design basically said it's all about the teachers. They came very close to doubling that number. Almost doubled it in a 10-year period. And how'd they do it? Through the teachers. They said, basically, if you aren't motivating students to like science, math, technology, engineering, if you aren't capable of teaching science, technology, math, engineering to these students, they're not going to get the degrees. So we don't want you as a teacher. So they started getting rid of the teachers that couldn't do the job. Now, that's the dynamic process. As the number of teachers that are capable start improving, you see that rapid increase until you reach some sort of baseline effect, or new baseline. But as the teachers start changing, it's that butterfly effect. Pretty novel idea. They looked at one subset and said, it's the teachers. It's all about the teachers. The conclusion, students start in elementary school, they go through secondary school, college, etc. Somewhere along the way, they either have to become interested in STEM, or they're going to lose interest. If they lose interest, it's very hard to get them back on track. Can someone get them back on track? Can you have a teacher motivate them? Can you have teachers keep them from losing the interest? It's all about the teachers. Teachers influence students. Teachers affect the capability, and it is a dynamic process. Teachers that are influencing students to stay in STEM, there you go. You're going to have more STEM graduates. Teachers that can affect the capability. If they teach them better science and math, you're going to have fewer that fail to succeed along the way. Only 40% of college students that start in one of those technical degrees actually end up with that technical degree. Are they teaching science and math at the high school level the right way so that they can succeed? And it's dynamic, like I said. Once you start changing one part of it, the teachers, then you see changes in the other part. This is a very small scope of what the overall effect could be. But it is one small subsystem in this gigantic system called the U.S. education system. So where would further research come into play? Well, I think they did a pretty effective job of targeting a lot of these areas. The scope of the initial study was 5th grade when they started getting interest in math and science through the undergrad, okay, to their bachelor's degree. But if you take a look at this level right here, the focus of this study was just on the teachers. Okay? The focus was just on the teachers. There are so many systems within this system that you can look at a lot of different things. My hope for my research, I would like to break that big box high school down into some smaller subsets. Does everyone need to take 4 years of English? Does someone who wants to be an auto mechanic need to be in the same classes of someone that wants to be a systems engineer? Does everyone need 3 years of math, 4 years of English, and 2 years of history? Is that just social concept? Is that legislature? Is that educators running the system? What if we let an engineer take a look and say, here's what you really need? Breaking it down into smaller subsets. Changing the scope. I said they looked at the teachers. What if you looked at the guidance area? What if you looked at the facilities, the programs of study? Does everyone need to be sitting in a classroom of 30 students like this? Or should somebody be in a different area based on their objective? Some students might not have college-bound aspirations. They may want to go right into the workforce. It may be their life's dream to be an auto mechanic. Do they need to be sitting in a classroom reading books by Edgar Allan Poe? Or should they be in a classroom where they're hands-on, reading books about proper ways to fix an engine? A lot of different things we can look at. And finally, we can all imagine how many different combinations you could come up with by combining all these little different changes and all these little different subsets. It's endless, it's countless. It's kind of daunting when I think about the research topic that I want to take. What makes things successful? Well, it could be a lot of little things put together. And there may not be one exact solution. There might be many solutions to one simple problem, and that is trying to make everybody work the same way. I would like to give accreditation to the different areas that I've looked at. On a daily basis, I am thinking about systems, okay? I think as an engineer. I've worked with educators, but I think so much different than they do. They think in terms of legislation and the requirements and how many classes students have to take. And I think of what's our goal? Our goal is to get them to an endpoint. So I'm always thinking in systems. And engineers, we think a lot different than other people. This book right here entitled System Design of Education sounds exactly like what I want to research. But it's written by educators. It has nothing to do with the engineer's view of things, of the inputs and the outputs and the requirements, and setting up a standard and being able to model it. It's based on legislature. I'm very thankful to Dr. Cohen in the Systems Engineering class for helping put me onto this article. Again, systems engineering in the U.S. education system. Very nice to see that it has been broached, that the area is there, and that I have a great start in my literature review for my research topic. Thank you very much. I'm on campus all day. I hope to be able to visit again soon, and I appreciate everything that's being done for me in this class. Thank you very much.
Did you just finish? I was going to say, just ignore the girl in the corner.